Hi everyone. Today I'm going to present our final project for class 6775, named a register scheduling framework. So this is done by our group, including me, Miaohui, myself, Shuzhe, and Tongyuan. So we have already discussed what scheduling is. So we'll directly jump into our problem. Uh, so we will be focusing on the problem uh, that's only focusing on the register and time constraint. So each operator only runs for a single cycle and there's no chaining allowed. By only focusing on register and time constraint, we mean that we want to minimize the register usage given the time constraint. And also it's dual problem. We want to minimize the time given the register usage constraint. So what does register usage and time constraints means? So in this example, in the specific schedule example, we want to schedule these four operators. So we schedule these four operators into three different time slots. Therefore, the time usage for this schedule is three. And register usage is the number of registers needed to carry all the output from previous cycle to the next cycle. So for example, for the second cycle, we need to carry the output from V0 and V2 to the third cycle. So that would be 5 plus 4 equals to 9. The circle inside each operator is the number of registers needed to carry the output of this operator. So the total register needed will be the maximum of the register needed across all the cycles, since we can reuse the register once this cycle is finished. So in this case, the register usage will be 9 for this schedule. Next, we'll talk about two methodologies we use to solve this problem. The first one is integer linear programming. It guarantees optimality given enough time. However, it has a worse scalability due to its NP-hard nature. And the other one is force-directed scheduling. This is a heuristic-based method. It has a better scalability, but it can be suboptimal in some cases.
I will talk about our two formulations. In both formulations, we assume that all operations start from index 0 and clock cycles start from index 1. In the time constraint formulation, we first need to define the variable v and s, which means the operation n is scheduled at cycle s if it is equals 1. And from this variable, we can derive the second variable Vn, which represents at which cycle the operation n is scheduled at. And we also need to derive YIS and ZIS. And YIS means the operation I is scheduled before or at cycle S. And the variable ZIS means the operation I is scheduled after cycle S. In order to calculate the number of registers used in each clock cycle, we need to define the variable LIS, which means the output of operation I is left at cycle S. And we have an example on the right in the blue text. You can check them later. For the constraints, we have four of them. The first one is that all operations should be scheduled at a certain clock cycle. And the second one is parent operation should be scheduled before its child. The third one is for each clock cycle, the number of registers used should not exceed R. And the last one is the boundary for Vn. Our objective function is to minimize variable R. This page is an example of the time constraint formulation. On the left, the time limit is 2, and we need to use at least 9 registers to schedule these four operations. However, if we increase the time limit to 3, the minimum number of registers used to schedule these four operations is 7. Now let's talk about the register constraint formulation. The register constraint formulation is very similar to the time constraint formulation, where they have the same number of variables and their definitions are exactly the same. However, for the constraints, because the register is a constraint, we need to provide it as a constant. So the third equation is a little bit different. And also, the time here is also a variable. So the boundaries for the time and Vn is also different from the time constraint formulation. And the objective function is to minimize the time, which means minimize the maximum of all Vn. And here is the example for the register constraint formulation. On the left, the register limit is 9, and we need to use at least 2 cycles to schedule this for operations. However, if we reduce the register limit to 8, because we don't have enough registers, we need to we need at least 3 clock cycles to schedule them.
Now I will talk about the force-directed scheduling. This scheduling technique is a heuristic with the goal of reducing the resource usages by balancing the concurrency of the operations assigned to them. So concurrency balancing helps to achieve high utilization of resource units, and that will lead to minimizing the number of resource units required at each time step. There's 3 major steps to this algorithm. The first is that we determine the ASAP and ALAP scheduling of each operation, and by combining them, we will have the time frame of each operation. Next, we will calculate the distribution graph of each operation, which will indicate the concurrency of similar operations. And then lastly, we will calculate a self force for each node. A force for each operation at each time step will reflect the effect of scheduling that node in that time step. And the effect of that on the overall operation concurrency. If it is positive, it means that the assignment will cause an increase to operation concurrency. And if it is negative, it leads to a decrease.
Then I will go through the benchmarks and tools we use for the evaluation of our scheduling algorithm. Our first benchmark focuses on small randomly generated text. Here we use a Python script to control parameters such as the number of nodes, node weights, and the probability of edges forming between nodes. This approach lets us tailor the complexity of the graph and verify our method's correctness. Next, we scale up to large synthetic random workloads sourced from an ICML paper. These are significantly larger, often comprising thousands of nodes. By challenging our solver with these large complex graphs, we test its scalability and robustness. Unlike the smaller DAGs, these workloads are designed to push the limits of computational complexity, and we'll see whether our method can handle real-world scale problems and still deliver strong performance. Then, to bridge the gap between the static and the real-world cases, we use the EPFL benchmark suits, selected 5 moderate-sized circuits larger than or small decks but still manageable, making them representative of practical industrial scenarios. In these circuits, each node only contains 1 base data, so the number of nodes can be directly used to represent their size. Evaluating or solver all these benchmarks demonstrates its practical applicability in real engineering workflows. Next, I want to highlight the 2 ILP solvers we used as baselines for our evaluation, CPC and Globy. CPC is an open source solver associated with the CoinOr project. Globy is a commercial industry standard solver. By comparing our solver against both CPC and Globy, we can directly assess how well we perform in terms of solution quality and computational efficiency. Assuring that our method stands up to both a well-established open source solution and a leading commercial option.
Next, I'll talk about some setup in our evaluation. First is for time constraint problem, we set the time limit to be the depth of the input data flow graph. That will be the minimum achievable time step. And then for the register constraint problem, we set the register limit to be 1.5 times the minimum achievable registers obtaining from the previous dual problem. And we set all the RP solvers have a timeout to be 900 seconds. And for the force direct scheduling, we currently use a Python-based sequential implementation. So here's the results on time constraint problem. As we can see, Groovy almost achieves the best performance on all the graphs. Although sometimes it runs out of 900 seconds, and it also cannot obtain any legal solution on this one specific graph. But overall, the performance is good. And for CPC, it cannot achieve legal solution on any of these graphs. And for force direct scheduling, it can obtain legal solution for the most cases, and it sometimes outperform Ruby with less time. Next is results on register constraint problem. So this formulation is more difficult for the RP solvers. Even Groovy can only obtain 4 legal solutions across all the benchmarks we have, and CPC still unable to achieve anything legal. So here come to our conclusion. So Groovy demonstrates very strong performance on all formulations and benchmarks, and CPC unable to solve any problems in our benchmarks. However, we have verified its correctness on toy examples. And for force direct scheduling, it produces higher quality solutions in some cases compared to RP solvers. However, the current implementation is not optimal due to our implementation caveats, but we're still working on it. So that will be all of our presentation. Thanks.